Okay, so here we've got a lawnmower with a couple of different, well, a few different forces on it. So we're going to try and work out force B here, okay? So essentially what's happening here is you've got the weight of the lawnmower acting downwards, 350 newtons, and then you've got somebody at the front of the lawnmower and somebody at the back of the lawnmower, so to speak, lifting the lawnmower. So these forces B and A are forces of people lifting the lawnmower. So we're just going to try and work out force B. And the way we're going to do that is using the principle of moments, okay? So when this thing is lifted, it's held above the ground. We're going to say that it's stationary, held stationary above the ground. So we know that the sum of the clockwise moments has to be equal to the sum of the anti-clockwise moment, okay? Sorry about that messy M there. Now, it looks quite difficult here because you think, well, for a moment, to do a moments problem, we need a pivot point. So where's the pivot point? Well, you can actually take the pivot point to be a couple of different positions. You could take it to be B, or you could take it to be A. And we're going to take it to be A. We're going to say that this lawnmower is pivoting about the position A where somebody is holding the lawnmower, okay? They're holding it there, and we're going to say that that's the pivot point. Okay, so if that's the pivot point, then we've got two forces that we need to consider that are causing moments. This force here doesn't have a moment because the moment is the force times the perpendicular distance from the pivot point. That force is acting at the pivot point. So there's no perpendicular distance, there's no moment from that force. So the only two forces to consider are the weight and B. So weight is pivoting this thing clockwise, and the force B of this person lifting the lawnmower at the handle is pivoting it anti-clockwise, okay? So the clockwise moment here is going to be the weight force multiplied by distance. Now the distance from A is 20 centimetres. Now because both of these are in centimetres, we can either leave them in centimetres or convert them to metres, it doesn't matter. I'll just leave them in centimetres here. So 350 times 20 is acting clockwise. Now anti-clockwise, we've got force B multiplied by its distance from A. Now its distance from A is 90 plus 20, which is 110 centimetres, okay? So 350 times 20 gives us 7,000, okay? So if you put that into your calculator, you'll find that 350 times 20 gives you 7,000, but you should be able to do that just from some simple mental maths there, okay? And that's going to equal 110.0 B, okay? And therefore B will equal 7,000 divided by 110.0, which gives us, if we take 7,000 divided by 110, that's going to give us 63.63. So we'll round that to 63.6. So 63.6 newtons, or you could round it to 64 newtons because that could be 2 sig fig. We're not sure. These are 3 sig fig. So I suppose it would make sense to make it 3 sig fig, as those are 3 sig fig, and that's potentially 3 sig fig as well. Okay, now we could then look at trying to calculate force A. So to do that, we know that this situation is static. We know that the force is lifting this object and the weight acting downwards must therefore be in equilibrium. So we know that the resultant force on this object must be 0 because the object is stationary, it's static. Now, if we are saying that weight is the only force acting downwards and these forces are acting upwards, we know that the force B is 64. So we basically know that force A plus 64, so those are the two forces acting upwards, must be equal to 350. Okay, and therefore A equals 350 take away 64, which is going to give us 286 newtons. Now we can confirm whether that's correct as well, because we can look at moments about this point here. So if I change maybe to the red pen, we're going to do moments about this point now, okay, about point B, this point here. Sorry, that's just messed that right up, but there we go. So we're taking this as our pivot point now. So we've got a clockwise moment and an anti-clockwise moment. So the sum of the clockwise moments must equal the sum of the anti-clockwise moment. So the clockwise moment in this case is 350 multiplied by 90. So, sorry, I'm just moving the paper there. So 350 times 90. That's the clockwise moment because this weight is acting 90 centimeters from the pivot. And then here we've got is equal to A times, A is the force here, multiplied by the distance, which is 110. So remember, this time we're taking that as the pivot. This is 110 from the pivot. Now remember, force B does not provide any moment because it is at the pivot point. There's no perpendicular distance from the pivot point that this force is acting at, and therefore there is no moment caused by that force. So if we solve this now, 350 times 90 is going to give us 31,500. What am I doing? 31,500. Okay, so we're just coming over here is equal to 110A. So therefore A is going to be equal to this divided by 110. So we're going to divide that by 110, and that gives us an answer of 286 newtons. So that just confirms the fact that this is definitely 286 newtons. Okay, so that's how we do that one.